Good afternoon, dear colleagues. I am going to tell you about the work of two students at Complutense University of Madrid, Daniel Beltrán and Gloria Tejedor. This is to be presented at the June meeting of the Nuclear Physics Division of the Einstein Telescope Observational Science Board. I am going to show you why gamma rays from cataclysmic events arrive to Earth without measurable delay respect to gravitational waves. That is, in a manner of speaking, I'm going to show that light travels at the speed of light, which is not always trivial, as I hope you will see in what follows. Now, the motivation is this beautiful measurement of gamma rays in these three histograms at the top that arrived to Earth in 2017, just 1.7 seconds after the gravitational wave chirp at the bottom. This is amazing, because the travel time to the galaxy where the neutron-star merger happened is 130 million years, so that is a delay of a part in 10 to the minus 15. This is usually interpreted by the absence of anything between that galaxy and ours, and what delay there is must have originated at the source, because it was for a while transparent to gravitational waves but opaque to photons, that were emitted later, as this sketch shows. Now the Einstein telescope will reach much farther back in time, so that the gamma rays can swipe a more significant, a longer column of vacuum and perhaps hit on the way an electron or a background photon. So here are the cross-sections of the various processes. Gamma electron Compton scattering, the green line, with its constant classical Thomson limit at low energy and its 1/e square behavior characteristic of QED at higher energy. Then we have at the bottom elastic photon-photon scattering. This is tiny, given by quantum corrections to the Maxwell equation. The threshold of electron-positron per production, however, allows photon-photon collisions with sizable cross-sections, the Breit-Wheeler process given here by the blue line. Now, if you thought that the proton beyond the electron played any role, remember that at low energy in the center of mass, they are suppressed by the small ratio of their masses. So, in this work, we have been learning why these possible scattering processes do not stop gamma rays from arriving on time, and that's what I'm going to show you. Let us first look at high-energy photons, for which the pair production Breit-Wheeler process dominates. For tera-electron-volt photons, the optical depth shown in the plot is huge. Remember that it enters in an exponential that suppresses you the number of photons. This means that there is a gamma-ray horizon. If you fix your photon energy and slide towards the right to increasing redshift on this plot, you will run out of far sources in the sky. Its Blazar source in this plot is a dot. Photons just don't get here anymore. But this plot is entirely within the reach conceived for the Einstein telescope, so deep gravitational wave events cannot be accompanied by ultra-high energy photons. So what these photons are colliding with is extragalactic background light. These are small amounts of optical, infrared, or ultraviolet photons streaming nowhere away from the galaxy that emitted them, together with the cosmic microwave background. Now, if one of these photons collides with a probe photon from the cosmic rays, it can create an electron-positron pair. There are many microwave photons, but the center of mass energy of the collision with a tera-electron-volt photon is insufficient for pair production, so that absorption is dominated by stellar photons emitted in the infrared and above. Let's move on to the time delay. To compute it, we need to integrate backwards in time, which we will take as integrating forward in redshift. And the refraction index depends on Z, both because the density of target changes and because the probe photon was more energetic in the past. Now, the index of refraction is just another way of seeing the dielectric constant, which is its square. Absorption comes from its imaginary part, normally small, and refraction from the difference between its real part and 1. Now, the real and imaginary parts of this dielectric response are not independent. They are linked by the Kramers-Kronig integral relations here. It is sufficient to know either of the two parts as a function of frequency to obtain the other. The reason for this is causality. The response function, in blue, g of tau, between the applied electric field and the medium displacement response d, has to vanish for negative times. The cos d cannot precede the cosine E. Therefore, its Fourier transform, when omega has a positive imaginary part, is analytic. The exponential becomes a convergence factor. So you can apply Cauchy's theorem to the dielectric function in the upper plane, and the Kramers-Kronig relations follow from this Cauchy's theorem. So here is what my students did. Starting from the measured optical depth, blazars farther away look dimmer, they obtain the imaginary part of the refraction index. The Kramers-Kronig relation then gives them the real part by numeric integration, and from this we can get the modified velocity of light, and thus the time delay. Now cosmology enters in that the integral towards the past requires converting time to redshift, and we use for this a standard cosmological model with matter and cosmological constant in the non-proportions, and also in the dilution of background targets. And here is the imaginary part of the refraction index. First, you should see that it is tiny, 10 to the minus 46. Its energy dependence shows a broad peak because photons of about 20 GeV can find sufficient infrared photons to collide with and produce pairs. Then there is a second peak for lower energy gammas that we attribute to their colliding with abundant Lyman alpha photons from the hydrogen atom. Because it is in the ultraviolet, it can disperse lower energy gamma rays. Apply the Kramers-Kronig relation, and the real part of the refraction index has the same shape, and it is also very small. Immediately, we can get the time delay, here for two photons of 0.1 and 10 TeV, upon being detected, of course, and as function of the source that emitted them, how far in redshift the source is. The delay is negligible, as you can see, of order 10 to the minus 26 seconds. Upon crossing the whole visible universe, we are getting really nothing. Well, let us have a look at lower energy gamma rays, of interest for neutron star mergers, for example. Because at the mega-electron volt energy in center of mass or below, pair production is not possible, Compton scattering dominates. Because there is no absorption data in this regime, we must turn to theory. So here is again the graph with the various cross-sections. We use the leading order cross-section shown in the first line, and use its known limits as checks of the codes. Now this slide is a bit busy, just to remind you of the baryon density in the universe, which we take equal to the electron density that we need. Given the cross-section, we can use the cosmological model to obtain the optical depth on the second line, and at the bottom, the imaginary and real parts of the refraction index, the latter obtained from Kramers-Kronig, and where a bunch of constants have been grouped in this A. And here is the corresponding expression for the time delay. We evaluate it numerically and find it to be still tiny. We can give you the dependence on the redshift and the energy, but they don't matter because it is so unmeasurably small anyway. So you can ask yourself at this point, as I did when I launched this little project, how can you have absorption without refraction? Causality connects them. And by the way, you may have heard of refracting gamma rays a few years back in the laboratory in the Llanes-Estrada Institute. Here on the left you see two beams, one in free propagation and one going through a material, and there is a slight deflection angle of order a millionth of a degree. So people speak of nuclear photonics, and there are some groups investigating gamma ray lenses. So why does this not happen out there in space? Well, let's compare the optical depth, absorption, and the fractional time delay, refraction. Both are dimensional quantities, and as you can see, both are linear in the refraction index, n, whether the imaginary part or the real part. And these parts are commensurable by the Kramers-Kronig relation. However, there is a difference between the two formulae. The top line, the optical depth, displays a factor of the energy of the photon divided by the Hubble constant. This, however, cancels in the ratio of the bottom line. That the top line has an extra photon energy is known from optics. It is some version of the Beer-Lambert law between the absorption coefficient and the imaginary refraction index. If we convert the length scale in that attenuation coefficient, which is just the derivative of the optical depth respect to L, the distance, into the redshift, we get this normalizing factor, H0 over the energy of the photon. So here in the box you can see our answer to why refraction is negligible. Both the incremental real part of the refraction index as well as the imaginary part are found to be tiny for gamma rays, but while the real part directly gives negligible delay, the imaginary part is multiplied by this large factor, yielding sizable absorption, at least for GeV-TeV photons. In conclusion, we have given a fairly understandable derivation of why gamma rays do propagate between galaxies at extremely nearly the speed of light, so we can have tiny refraction even with sizable absorption. The numeric factor yielding this imbalance is the Hubble constant over the photon energy, and here are the ranges. So a factor 10 to the 40, compensating the smallness of the refraction index, is possible and yields measurable absorption. But we expect no delay because this factor is absent, so that gamma rays should travel on time respect to gravitational waves. Only that 100 plus GeV photons will be absorbed in cosmic distances, something akin to the GZK cutoff for protons, if you know what this is. So anyway, thank you for your patience, and I hope you found something useful in this little lecture. Yes, gamma rays travel to Earth on time.